Thank you. I'm going to tell you about the all-sky automated survey for supernovae, or ASAS-SN. We've already heard about a bunch of discoveries that we made throughout this conference, but I want to kind of give you an idea about what the survey is all about. But the kind of theme of my little spiel is basically that bigger does not necessarily equal better. So that's not to say that the opposite is true, by no means. If you want to go through some difficult terrain or some mud, you probably want some big SUV. But if you're going across the country and you want to be fuel efficient while you do it, then maybe a smaller car is better. So don't make this mistake. Don't necessarily equate bigger with better. The scientific goals of ASAS-SN are really to monitor the entire sky with as fast as cadence as possible. We do the entire northern hemisphere, we do the southern hemisphere, we do the galactic plane, we do out of the galactic plane, we do everything. And this is the first time in human history that this has actually being done. Currently, we have a cadence of about 2 days over the entire sky. About half the sky is in an overlap region between two of our fields. And so actually about half the sky, we actually have a cadence of about 1 day. We strive to make all of our discoveries public as soon as feasible, as soon as we possibly can. We have long-term goals of making all of our data public as well. That takes people, and so that'll be a little bit slower coming, but that is a long-term goal of this ASAS-SN. We really want to be a public survey. Completely public survey. To do this for a reasonable amount of cost, you have to make some limitations. We survey the entire sky down to about a limiting magnitude of about 17. During new moon, we go deeper. During bright moon, we go a little shallower because we're actually sky background limited. To do this, we want to use commercially available telephoto lenses and CCDs. I mean, that is what we use. We do this to basically keep costs down, and it also allows us to quickly expand to more sites as more funds become available. We can just go and buy Nikon telephoto lenses, buy some amateur CCDs, and voila, you've increased your cadence. And then finally, the prime scientific goal of ASAS-SN is to really be an unbiased supernova survey. So I hope to show you that we're doing a pretty good job of that already on the bottom plot here. These are all the supernovae discovered in 2015 that were brighter than 17th magnitude, that peaked brighter than 17th magnitude. On the axis, I give you the host galaxy K-band luminosity, so it's a proxy of stellar mass, so big galaxies over here, small galaxies over here. On the y-axis, I show you the offset from the center of these galaxies that the supernovae were found. So right at the center is down here. This is 1 arcsecond. And then far outside the galaxy is shown at the top. And I broke down the sample in 3 different samples. There's ASAS-SN shown in red, so all the red is ASAS-SN. Blues are all other professional surveys combined, and black are amateurs. So there's 3 things I want you to get from this plot. 1, there's a lot of red on it. ASAS-SN is doing quite well. 2 is that ASAS-SN and other professional surveys as well find supernovae in big galaxies as well as small galaxies. Most professional surveys now are not galaxy targeted, so we're doing a very good job of surveying the entire sky. Amateurs, of course, are biased to larger galaxies. But the real surprise is probably the 3rd one, and that's that these horizontal dashed lines, you can see black, blue, and red for amateurs, professionals, and ASAS-SN, show you the median offset from the center of the host galaxies that these supernovae were found. So what you can actually see is that even though we have very large pixels, we actually find supernovae about a factor of 2 closer to the center of the host galaxies than all other professional surveys combined. And this basically means that we do very well because it's much harder to find supernovae at these locations. And so this is a testament to our image extraction pipeline, and this fact will come up when I talk about our discoveries in a little bit more detail. If you want to break that down by group, these are basically the same supernovae broken down by who discovered them. So you can see, again, that ASAS-SN is doing very well compared to these other surveys. Amateurs also do a great job. There's a number of very dedicated amateurs as well. So finally, I'll just go through and quickly list, because I don't have time, I'll list some of our more exciting discoveries. We have many papers on a lot of things. We have over 300 supernovae now. We detected ASAS-SN 14LP, which was a 1A. We detected it less than a day after explosion. So as we've heard a number of times in a number of different talks, finding transients early is very important. And if you're looking for the brightest transients on the sky, you want to find them the earliest. Currently, our surveys are not held back by depth. We're held back by cadence. So you want to go to faster and faster cadence to find the brightest objects every year as early as you possibly can. We've discovered ASAS-SN. I won't mention any more about that. That's been discussed pretty heavily in this conference. We've discovered hundreds of CVs and novae as well. I think this is actually an area that is going to become even more exciting in the upcoming years. It's had its heyday in the past, but I think it's going to become even more exciting looking towards the future. I guess I was a little disappointed that these weren't discussed more during this conference. We have young stellar objects in Outburst 2. You have XOR-like events, FU Orionis. There's a bunch of exciting objects here, and they're teaching you about how actually stars assemble their mass very early on in their lives and tell you about disks and interaction. So we have a number of interesting discoveries here. As was just mentioned, I was very happy to see this. In the previous talk, large stellar flares are quite interesting. This is especially true because TESS is supposed to launch next year. And we're going to start finding planets around these M dwarfs, so we're going to want to know, are they habitable or not? And so ASAS-SN is actually primed for finding many of the largest M dwarf flares ever detected. We've detected 2 of the largest M dwarf flares ever detected. These were more than 9 magnitude flares, and I would posit that if you're living on the surface of a planet around one of these stars and then it puts out 3 to 4 months of its energy in an hour, I don't think civilization would continue to exist. So I think that's quite interesting for this. We've actually detected the second L dwarf flare ever detected, and this was actually 11th magnitude L dwarf flare. This is a huge flare. The previous flare was only detected by Kepler. There's many AGN blazar flares. We have an interesting change of look object we found. There's a lot of science here as well that I'm not going to dig into. And then finally, sources that have been discussed, again, pretty heavily in this conference, are the ASAS-SN TDEs. So we've detected the 3 closest and brightest TDEs discovered in the optical. And again, because they're close and they're bright, you can really get a huge amount of follow-up data on these objects. You don't need to go to 8-meter class telescopes just to get a low signals noise spectrum. You can get a high signals noise spectrum with a 2-meter and really study these objects up in detail. And it's these objects really that also show just how well ASAS-SN does at the center of host galaxies. Obviously TDs are at the center and they're hard to discover because of this, and we do quite well. And so I think that's probably all my time. So
thank you, Ben. And we'll move on to Armin Rest that will discuss Atlas.
Yeah. Hello, everyone. I will tell you a little bit about Atlas, which is a new survey that is just coming online. The PI is John Tonry in Hawaii. What pays the bills is the search for near-Earth asteroids. So NASA has been funding this. But if you would look at the list of the PI and the co-Is, these are all people that are also interested in transients, and that's why I'm involved in this survey. So we have right now 2 half-meter telescopes, one in Haleakale and the other one in Mauna Loa. Our goal is to cover the whole sky, very similar to ASAS-SN, as often as possible with a very good cadence to find the supernova in the early stages. We have broad filters. We do have to find the near-Earth asteroids, and so we are a little bit limited in our choice of filters for the general survey. So we have this kind of like blue or greenish filter and reddish filter that are very broadband, but we can get some color information from that as well. We will go to the red filter in general when the moon is up, and the greenish filter when it's dark time. We do have 16 filters overall, always installed, so we can, or we plan to use them at some point, not as often as the broadband, but yes, we do want to look at some of the emission lines and the other colors. So what is the status? The first telescope we installed last year, and as you can imagine, it takes a bit of time to make everything work, to get it pretty much robotic, that we can use it, that nobody has to be there anymore. The one problem that we have is our Schmidt corrector has issues, and so instead of the 2.5 arc second full width half maximum, right now we have a PSF of 6 arc second. That of course gives us a hit. We do have a very nice CCD. It's a 10K by 10K, and it is a very good quality in overall. Not many flaws in it, good readout, good QE. That's a really nice piece of hardware. The telescope 2, we have everything in place. The only problem is that we are now waiting for the Schmidt corrector, since they didn't want to repeat the same mistake they have done with the first one. And that has been a little bit an issue. I mean, we have been trying to get the Schmidt corrector corrected since, more than half a year, but nearly a year. I mean, after we installed it last year, we realized that, that Schmidt corrector is not very good, and we were in contact with the vendor, and it just has been a little bit a difficult situation. But we hope that we can figure this out very soon. So, so we hope that in a couple of months we will have the new Schmidt corrector for telescope 1, and then soon after the one for the telescope 2. So hopefully this year we will have both telescopes fully operational. We're also in the process of putting in another proposal for 2 more telescopes that will be put in the southern hemisphere, probably one in South Africa, and then maybe one in Australia. We're still negotiating where we want to put it. So right now, when we have a good night, we have about 800 images, and each image is 30 square degrees. So we cover 6,000 square degrees 4 times in a given night. So 4 times is because we look for asteroids, so we want to go back 4 times to the same field to find the asteroids. Of course, as soon as we have the second one online, then we will basically have the cadence of every 2 days we will go back to each field and then have 4 epochs. So I think this will be a very nice cadence. The current detection limit is about 19 for 50% completeness. When we look for the asteroids, we basically take everything down to 18.5. After we get the new corrector, and we will have hopefully a significantly smaller PSF, we should be able to go down to about m equals 20 in the optical. In the last few months, we were finally fully online and have basically taken observations every night that the weather allowed. We found 11 NEOs, 4 of them potentially hazardous, 2 comets, and we have submitted about 330,000 observations of 27,000 unique asteroids. After we have gotten all of the solar system objects under control, we are now working on getting the stationary transients all lined up that we can follow them up. We have already observed some of them, a few supernovae. We also have submitted some of the photometric transients to the transient server. So I really hope that in the next couple of months we will be able to get this all very automated, and then as soon as possible we will also go public. And so I hope you will then follow these supernovae up. Thank you.
Thank you, Armin. The next will be Djorgovski speaking about CRTS.
Okay, so I'm to tell you about the greatest little survey nobody knows about. It is a survey that's piggybacking on a search for Earth-crossing asteroids run by people at Lunar Planetary Lab in Arizona. And they're very successful at that. They found like 2/3 of all known near-Earth objects so far. So we tap into their data stream for free. They keep everything inside solar system. We take everything outside solar system. The drawback is that we do not govern the cadence. The cadence is optimized to find asteroids with 4 exposures spaced by 10 minutes per field per night. But then there are repeats, so there is kind of quasi-logarithmic sampling of time baselines. And the data now span 10 years or more. So you get time baselines from 10 minutes to 10 years, and a few hundred exposures or epochs per pointing anywhere of about 80% of the sky, which I think really is still a unique data set for time domain exploration. And as time goes on, it's becoming clear to me that it's really the archival stuff that's going to be the most exciting as we accumulate more of these data. Because we're all looking for transients, we're all finding the same things, and all of us can fall at most couple % of all transients that we find. So you can see the numbers here. And I think probably the most important thing from your viewpoint is that the data are open. Anybody can access Catalina data. You can subscribe, or you or your robots can subscribe to electronic alerts in real time. If you're not in such a great hurry, the next morning you can look at the annotated list of transients, they link all of the archival data and whatnot, and there is an archive of light curves. I will not even attempt to go into the science that's been covered, but there is something for everyone there, and you can just look at it yourself online. One thing I'll point out, we do have essentially ongoing monitoring of about 500 million sources in the sky. Essentially down to the depth of the old Palomar sky surveys, everything except the galactic plane and celestial poles. And that, I think, is truly unprecedented one. One of the results from this was mentioned earlier today, having light curves for all spectroscopically known quasars, like 350,000 of them, led to the discovery of the binary supermassive black holes and some other interesting stuff. Incidentally, we're working on producing a new catalog of a couple million additional quasar candidates over the entire sky in the basis wise colors and CRTS variability, because we need more quasars. Lots of stuff has been found out. We have over 12,000 high amplitude transients. We have an operational definition of what is a transient in terms of the contrast and significance and so on. And it's basically strong transients. When LSST people talk about 10 to the 7 transients per night, meaning any statistically significant change in flux of anything, I find it to be completely silly. I think that's basically transient spam, because even with these high contrast luminous ones, we can only fall a few percent. And all these other things. And as I said, these 500 million light curves is probably where all real gold is, and we're just beginning to scratch the surface. We have like 13 million variable stars, and I don't know, tens and hundreds of thousands of periodic ones, and that's just limited by the output of the neural network by the name of Andrew Drake. He's the one who does all the heavy lifting. And there are 3 URLs here that you can go and get yourself the data. The main one then leads to all the others. That's where you find nightly annotated tables of transients with all the links and stuff. The next one gives you all the light curves in cone search. It's limited by machinery and throughput. And I think most importantly, our collaborators in India and UCA have agreed to be a worldwide server of this data forever, because A, we don't have money, and B, we're bored with it. But they will also serve image cutouts, and we know that you can improve photometry by at least factor of 2 or 3 relative to the pipeline photometry that's used for real time. And so also joining, I should point out that we hope to be joining analysis with a lot of PTF data. We've been already working on that, because there is no reason why we shouldn't. And so the last line here is to remind you that data may be free. That doesn't mean they're worthless. Okay? So people usually kind of tend to be biased about this, but we're in the new era. I mean, we're going from data poverty to exponential data overabundance, and it used to be that ownership of the data was the currency of the realm, and now the data are becoming free, and ownership of the expertise is where all the value really is, which is how it should be.
Thank you, George. And we'll move on to Eric Bellm that will speak about ZTF.
All right, thanks. So you heard a little bit about the motivation for ZTF from Sri last night. I'm the project scientist, so I'm in charge of the incremental implementation of this grand vision. The genesis for ZTF, it's a natural successor to PTF, which has a 7¼ square degree field on the Palomar 48-inch Schmidt. We used a second-hand camera for that with a missing CCD. And so the idea is to fill out all the unused field of view and fill all of the area that was covered by the Palomar Sky Survey photographic plates with CCDs. And so you can see in this top right corner, here's the PTF camera, and then this is a rendering of the ZTF camera. So out of a 47 square degree field of view, 16 6K by 6K E2V CCDs. So that's about a factor of 6 improvement. We gained another factor of 2 from faster readout. The modern CCD controllers are faster, so we can read out in about 10 seconds instead of 30-something. And so the net impact is more than an order of magnitude improvement in survey speed, both in area and in volume. And so that lets you do a survey that's wide area, but also relatively high cadence to find things that are both fast evolving and rare. So we can replicate the Palomar Sky Survey in about 8 hours if you didn't have to worry about the sun. And if we did just a sort of a uniform average survey across the 3-pi sky, you'd get almost 300 observations for each field every year, which opens up a lot of variability science. The photometric precision is pretty good. So we have the CCDs, we have the filters. The performance looks good so far. We should be integrating those together in the camera in the lab here in the next month or two. And we expect to take that to the telescope then in the middle of next year sometime. So what's in it for me, you ask? There's lots of public aspects to this. We're funded at the 50% level by the collaboration, and then 50% by the NSF through the MSIP program. So we proposed a couple of public surveys. The first is sort of analogous to the Universal Cadence LSST survey, but obviously shallower and in fewer filters. We call that a Northern Sky Survey, sort of a 3-day cadence average wide survey. We're also going to do an extensive galactic plane survey. This is something we've piloted with IPTF. We think there's a lot of interesting variability science in the galactic plane. All of the ZTF data will be public on various timescales, and we've also started releasing PTF and IPTF data. All of the PTF images and catalogs and COADs are out as of last year. You can go and download them. Starting this fall, we'll start releasing IPTF data with the addition also of a light curve interface. So if you just want to type in your RA index of the thing you care about, you can get the light curve. So look for that this fall. During ZTF, of course, we'll release all of those same products sort of on the semesterly or yearly timescales, and we'll also have near real-time transient alerts coming out of those public surveys. Finally, I want to highlight every summer we're having summer schools that are targeted especially at graduate students or maybe postdocs who are new to the field. We bring them in for a few days to hear science talks on where the frontiers of time domain are, as well as do detailed hands-on sessions with data analysis, learn some of these methods, and really trying to prepare a next generation of students who will then go on to be leaders in the LSST era. So this year's is in mid-July. Registration is open, so if you have students who are interested, please have them sign up. And you can learn more about all of this at our website. Finally, I wanted to just do a little comparison with other surveys. This is from a paper I put on the archive a week or two ago. One of the challenges in comparing time domain surveys is you can always change your cadence and hence your sky coverage. And so this is sort of looking at that trade-off, but in volume. So if you start at short cadence, you're covering a small sky area, and then you get a volume from the limiting magnitude of the survey. You can go slower and cover more area and hence more volume, but at a certain point in time, you run out of new sky. And especially for surveys like Atlas, like CRTS2, like ZTF, that happens in a night or two. And so there's a fundamental limit to sort of how slow you can go. So for all events, obviously the volume you probe, LSST is this blue line here on top that's going to discover the most events of any kind. But if you're interested in events that peak at magnitudes brighter than 21st magnitude or so, in fact, ZTF is going to survey the most volume for those events. And so we think it's really interesting for these sort of spectroscopic bright events that are most valuable. Thanks.
Thank you, Eric. And we'll move on to Ryan Chornock that will speak about pan-stars.
Okay, so pan-stars, at this point, we're going to sort of make a transition in the type of survey we're talking about from the sort of smaller aperture discovery sorts of surveys where you have to get triggered follow-up to the sort of larger aperture telescopes, deeper surveys where the follow-up in many cases comes from within the survey itself. It's a different sort of strategy. So Pan-STARRS 1 is a 1.8 meter telescope on Haleakala in Maui. Has a 1.4 gigapixel camera covering a 7 square degree field of view. The Pan-STARRS is a filtered survey with Sloan-like filters, GRIZ, and with a Y-band filter like LSST out about 0.95 microns. It's currently in a transition regime between the original Pan-STARRS-1 survey, which went from around early 2010 to early 2014. There's a second Pan-STARRS telescope that's being built next door. It's waiting for a camera. The exact timeline and details of what will happen with the Pan-STARRS-1 plus 2 telescopes are still a bit nebulous. And the intervening time is currently spending most of its time on a search for near-Earth asteroids. Those near-Earth asteroid images are taken mostly in what's called a W filter, G plus R plus I. But the group led by Stephen Smart at Queens is subtracting them versus Pan-STARRS reference images, and so they're still finding transients, the Pan-STARRS survey for transients. And approximately 10% of the time is actually doing, interesting science. Ryan Foley has gotten some supernova observations out of it. They're also spending time chasing after LIGO triggers, et cetera. So I wanted to say a bit about what the Pan-STARRS-1 survey did. So the Pan-STARRS-1 actually had a set of about half a dozen different sky surveys that they did, but the two main ones that you hear about are the medium deep survey and the 3Pi survey. So the 3Pi survey is the entire northern sky above declination of -30, and it was covered to a depth greater than Sloan, essentially. There was some time information. There were 2 visits per filter per year over 4 years. With weather losses, that means a typical spot in the sky had something like 6 visits per filter. And a lot of effort in Pan-STARRS went into the calibration. And thanks to the work of Eddie Schlafly and Doug Finkbeiner and collaborators, there's very well calibrated data that will be made public, hopefully, in a few months through Space Telescope. And if you want to hear more about that, please bug Armin, because he's very happy to hear about that. But basically, the point of my table over here is this is from a preliminary study showing of a small area on the sky where they went to the full survey depth, comparing Pan-STARRS to Sloan, DR8. And the limiting magnitudes in each filter are pretty similar in G, but by the time you get to the redder bands, Pan-STARRS should go at least a magnitude deeper. And it'll be full sky. But almost all the transient stuff that you've heard about on this conference came from the medium deep survey, which took up 25% of the observing time. And unlike some of the other surveys where they have a bit more flexibility in what they were doing, the medium deep survey was really designed to do type 1a supernovae at moderate redshifts. So everything in Pan-STARRS is not just a transient survey. There's about 12 different science key projects going from the inner solar system to the high redshifts. So it's trying to satisfy many science goals simultaneously, much like LSST will do. And so for the medium deep survey, there were 10 fields that were chosen around famous extragalactic spots on the sky, Cosmos Field, Chandra Deep Field South, et cetera. And when they were in season overhead, they were observed every night, barring weather. And it cycled through filters, G and R same night, then I, then Z, so you typically have a 3-day cadence to a depth of about 23.5 magnitude in each filter. So if you compare to the strawman plans for LSST, it's about a magnitude shallower, but a similar sort of 3-day cadence. And there's advantages and disadvantages to this, and you may have noticed that we heard Pan-STARRS transients mentioned in a number of different talks during this conference, and we didn't hear anything about type 1a supernovae, which is what this survey was designed to do. So in many ways, the science we did was working around a type 1a survey. So it's good that all the images were filtered, because in many cases, like with Suvi's TDEs, with the fast transients that Maria found, we didn't recognize right away that they were the interesting events that we thought they would be, but we had filtered photometry light curves for free. You just had to go back in the data and pull it out, which is a different mode of operation than the smaller aperture surveys, which require you to make sure you know something's interesting. However, we don't have control over cadence and survey. So if you want to use the survey itself, you're limited to the fact that maybe they missed I band or you only got G band, so you don't get your colors unless you go elsewhere for your follow-up photometry. And so many aspects of the survey are like a miniature LSST with 30 square degrees per night instead of 3,000 square degrees per night. So many of the problems that we encountered will be things that will be lessons for LSST.
Thank you, Ryan. We'll move on to Masao Sako, speaking about DES.
Okay, so I'll tell you a little bit about the dark energy survey. Should first warn that this is not a general purpose transient survey. It's a dark energy experiment. And it's designed to do 4 probes of dark energy, weak lensing, BAO, clusters, and supernova. The supernova data are useful for some transient studies, so I'll say a few more things about that. So we have a 4-meter telescope, the Blanco telescope in CTIO. The camera is a 500 million pixel camera with a 3 square degree field of view. It's called the dark energy camera. Filters, we have UG, RIZ, Y, and a VR filter, which is wider, and I believe we also have a narrowband filter, but the dark energy survey itself uses G, R, I, Z, and Y. We were awarded 525 nights over 5 years. We observed in seasons between early September, or actually late August and mid-February. And we just finished our 3rd year operations in February, early this year. It's also a community instrument, which means that you can write a proposal and get time on this using this camera. And that's that's been happening during most of the A semester and some nights during the B semester. It's hard to get time during the B semester because we're doing most of the observing. Here's some pictures. This is a filter, a single filter, a diameter of 60 centimeters. This is the focal plane filled with 62 2K by 4K CCDs, science CCDs, and a few focusing chips. Pictures of the telescope, lens, and the dome. Here's a picture. It came out. It's okay. So this here is one field of view, one DCAM field of view, which is roughly 3 square degrees. There are 3 shown here, which correspond to the 3 supernova fields, 3 of the 10 supernova fields that we observe every few days. And this is the size of the old camera on the same scale. And there's 1.5 billion pixels in this picture. Each pointing gives us a few 100,000 galaxies. And fewer stars, and so running image subtraction on these images is not trivial. There are 500 million things that could go wrong. This is my last slide. So I'll tell a little bit about the strategy, the observing strategy. So it has 3 components. Oops, sorry. 3 components: the wide survey, which covers an area of 5,000 square degrees. That's shown in red here. It looks like I don't know, looks like a weird shape. And we observe in G, R, I, Z, and Y. And the observing strategy is such that in each of the 5 filters, we cover a given spot on the sky 10 times. And so a given spot on the sky will be covered by, in one of the filters, 50 times during the 5-year survey. The depth per visit in GRIZY is shown here. So we are about 24.5 in G and much shallower in Z and Y. The exposure times are 90 seconds in GRIZ and 45 seconds in Y per visit. And at the end of the 5-year survey, we'll end up with about 70,000 exposures. Each exposure is about 5 gigabytes. We also have a set of shallow supernova fields correspond to a total area of 24 square degrees. So that corresponds to, so you see the little circles here. There are 10 circles here, 10 supernova fields. 8 of them are shallow. Exposure times are such that we get depths of about 23.5 to 24th magnitude per visit. And we visit every 5 days to 8 of these shallow fields. So a total of 125 visits over 5 years, 6,000 images after the 5-year survey. The deep field, there are 2 of them, one right here and another one right here. These are much deeper than the shallow fields, exposure times of about a factor of 10 more than the shallow fields. And in each visit, we go down to about 24.5 to 25th magnitude. And that gives us a similar number of images. The bright transients, so the data are not public, and it's not my decision, but the bright transients are public. So if you go to this web page, it gets updated in real time. We make all transients that are brighter than 20th magnitude available. So you'll see a list of about 20 or so that we discovered in the previous year. I don't know if anyone followed up any of our candidates, but if you did, let us know. Some of these bright transients are nice because we go very deep, which means that we discover these things very early. So for example, we have a type 1a that we discovered, I think, 6.5 magnitudes below the peak brightness, which is pretty amazing. So the supernova fields are really designed to do type 1a supernova, but you can also study type 2s, other types of supernovae, TDEs, and so forth. The wide survey so far has not been run through a difference imaging pipeline, but that effort is starting right now. And by the end of, I believe this summer, we'll have the first 3-year worth of images run through a difference imaging pipeline, and people are looking for high inclination trans-Neptunian objects, asteroids, Planet 9, which is supposed to be there, apparently, according to the Caltech people. And so we'll have those results out.
Thank you. And finally, we'll hear from Masaomi Tanaka that will speak about HyperSuprimeCam on Subaru.
First, I fully agree, bigger is not always better. But I have to talk about something biggest. And HyperSuprimeCam is our new wide field camera on the Subaru telescope. The Subaru telescope is a 8.2 meter telescope, and we have prime focus here. And 4 years ago, we installed a new camera called HyperSuprimeCam, and this camera is now being used for survey 2 years ago. And this camera has about 100 CCDs, and the field of view is 1.5 degree diameter, 1.77 square degree. So this camera can reach about 25 magnitude with 1 minute exposure. So this is a really deep imaging. So clearly the good thing is a large survey power or ATNU. So this lists up the ATNU of several survey transient telescopes. So Subaru HyperSuprimeCam has a large diameter and a large field of view. So if we calculate the aperture square and the square degree field of view, then this is the largest before SST. But as everyone already told, so this is not always good. And of course, a weak point is a spectroscopic follow-up is so expensive. And Eric has mentioned about, this paper. So extremely low spectroscopic accessibility. And also, Subaru is a common use telescope for community, so we cannot use this camera all the time for the transient survey. So this graph is true for a given observing time, but it's likely that we do not have much observing time. So clearly, it's better to focus some dedicated topics where really deep imaging are critical. So this is just a list of my thoughts. So this is really a powerful camera for high redshift supernova, and especially for superluminous supernova, we can detect up to redshift 4 or 5. So this is really the area where deep imaging are critical. And the time sampling is usually difficult to control for this kind of big telescope, but for high redshift object, this is not so critical. So high Z superluminous supernova is one of the most exciting stuff. And also for fast transient, so actually 2 years ago, we did the high cadence experiment using adapting the 1 hour cadence. So we observe the same field every 1 hour with this camera. So this is exciting because we can do this within a few nights or so. And the first result now can be found in this paper. But basically, the fast transient or high cadence, fast transient which requires a high cadence is also a good topic for this camera. And also for the follow-up for gravitation wave sources. So Brian already showed the kilonova emission is likely to be faint for 200 megaparsec distance. So probably we really need a 4 meter or 8 meter class telescope to do survey. And just give you a number, so we can obtain a good image with 25 magnitude for 100 square degree within 1 night. So this is really exciting for gravitation wave follow-up. So as I said, so this is a common use telescope. So available opportunity for you is now we are doing a kind of strategic survey or strategic program. And starting from 2014, we started the survey using 300 nights with this camera. And the supernova survey dedicated toward supernova, that we will have the survey starting from this year. So at the end of this year, we will start a supernova survey. And also, you can of course, submit your proposal. So I hope this will be exciting for some of you. That's all.
Thank you very much. I would like to ask one question, and then we'll open the floor for additional discussion. I would like to ask the panel, what are your thoughts about organizing the data? Obviously, we heard about many surveys that have different strength, but there needs to be a community-wide effort to organize this data in a way that would benefit the public component of the data in a way that will be available for people to access, and not just within each survey on its own, but in a more coherent way. Are there any thoughts that you might have about that in the era of big data?
So there's a lot of difficult questions you have to answer when you make your data public, right? Because many different people want their data and they have competitors, so it's a difficult question. But I was actually talking to James Guillochon during this conference, and I think it came clear to me that maybe as a community, we don't necessarily have to make every survey's images public, but at least where we're pointing, or you don't necessarily have to make that public, but at least searchable. So if you had, I covered this patch of the sky at this time down to roughly this depth, and it was all in one service, and then it was queryable, or even, so it's either that a user could go on and actually say, oh, I'm interested in a source that was about this bright at this location of the sky in this time frame, tell me all the surveys that have data there. That's one option. Another option you could also imagine is almost the reverse, where somebody queries and says, I'm interested in studying this object, and I will let whoever has data on it be co-authors, and then it just sends emails anonymously to all the surveys, and then they can write to the person who wants to do the study. So then at least you know who has data on what object. I think that's one of the biggest boundaries right now is if I have a particular patch of the sky, I'm interested in this M-Dwarf flare, and you don't follow M-Dwarf flares, then how will you know that this object is interesting, and how will I know that you have data? So I think that's at least the first step to what you want to solve.
Good points. Other comments, George?
Well, I think sociological problems are the only problems here, ownership of data. In terms of technology, this technology already exists. This is what Virtual Observatory was all about. Interoperability standards are there. The whole framework's there. In fact, I always say that time domain astronomy is sort of the microcosm of Virtual Observatory. So as far as that's concerned, we're done. Right? This is there. But persuading people to share data, especially in real time, is the real difficulty. I bypassed that problem with making a decision up front that we will make everything public right away, and that's that. I think most people should realize that it's irresponsible to clutch to your data when you can only do a few % of the science with the data.
Other comments, Aaron?
I think we shouldn't underestimate the technical challenges as we look at the next generation of surveys, particularly with ZTF and other surveys, DES, I'm sure, the cost of just hosting these data is non-trivial, and, there's the question of supporting long-term archives is, I think, a challenging one, and so, step one is the interfaces and the storage, but the funding, I think, is also an important issue.
Absolutely. Yeah, I definitely want to second that. It requires money and manpower, and nobody wants to do it, and nobody wants to spend money on it. But it's critical because of one thing that George mentioned, which is time baseline. That not just for if one transient went off and was seen by multiple surveys, you might want to combine it, but if you want to do a lot of science that goes beyond just watching one supernova, you want to connect DES data to Pan-STARRS data to LSST to Gaia, for instance.
So maybe a collaboration among the teams would be appropriate. Yeah.
So the DES data, all of the data are hosted by the NOAO archive, so you can go ahead and download all of our public images. The DES images go public 12 months after they've been taken, and it's there. You can download the first 2-year reduced images. Also, the DES collaboration makes an effort in getting the catalogs public as well. So we'll have our first year 1 catalog release pretty soon. So it takes time. You know, catalogs take time because calibration is complicated. You have to make sure that the survey is uniform, but we're trying to do that.
You mentioned that you have only the brightest ones publicly available, right?
Oh, so that's the transients.
The transients.
Right, but the wide field survey is making all the galaxies and stars.
Yeah, but we are here in the business of discussing transients.
Sure, okay. But the images are public after 12 months, so you can go back and look at things. We could make we did discuss the possibility of making all of our supernova candidates public. But we started with the bright ones, and apparently no one's looking at it, so why make, a 23rd magnitude transient public?
For HSC, we had actually discussion internally and in the collaboration. But for transient people, including me, I want to open the data, but many other people are included, and especially the galaxy people and cosmology people hesitate to open the imaging data, because once imaging data are available, basically anyone can do their own science. So I think that the situation is easier for especially for transient science, just to share the coordinate of the transient and the brightness when we discover, So I think that opening all the images is also technically challenging, but we have to coordinate the collaboration to share the target.
It sounds like one or a few postdocs that are talented and dedicated for this task could get this going. Yeah.
So
Armin,
you said you give me money, so.
Well, I'm sure NSF might be interested.
So let me put my Pan-STARRS hat on for a second. I know that lots of people have been waiting, and we have always like, okay, it will be, any time now and any time now. It has not only frustrating for other people, it has also been frustrating for us from PS1. But, asymptotically, we're getting closer and closer. And we are actually getting really close now. So all of the reductions, also photometry is done. And it is what it is. We are loading this photometry in the database right now. It will take about 6 weeks to finish that up. We already have all of the images, stacks, and individual warps at SDSCI. We have already the cutout server running that we internally use and within the collaboration. So we are only waiting now for the photometry to get loaded in the database and then to get shipped from the IFA to SDSCI, which takes another 2 weeks to 4 weeks. I mean, it's a lot of data. It really is a big data volume. So it's more than 2 petabytes. It is also expensive. We have to buy now new disks, and you try to get funds from NSF for that, because I think it's a service to the community, but it is not as easy. So the timeline is, I would say it's a few months. And we do have a lot of data. It is actually of pretty good quality. And I think as soon as it is public, lots of people will use it and will find it very useful. As for, in general, how to connect all of these surveys, in a way we have to think a little bit bigger. It's not only that for a single object, you then try to figure out if there's a baseline in some of the other ones. I mean, that takes a lot of time. What you really want to do is that you have a database query that not only can use, PS1 data, but then also can cross-correlate it to the other surveys, because you cannot do it on this object-by-object basis. And to do this, it is just very difficult, because it takes money if you want to host it at one place. It's sociologically, it's a very difficult thing, because I don't think everybody wants to give also there to one place. If it's at difficult locations, to connect it is also not easy, and at least not to make it easily accessible for the user. So I think we still have a lot of technological challenges there, how to do that. Do we have a centralized data repository, or do we have several places that we can then access easily with a good user interface? So, you know, I mean, as a community, if we want to get the science out, we really have to try to make this happen.
Yeah, from my experience is that if you ask this question, you ask young postdocs, they will find very good solutions on a relatively short time scale. It's just that, you know, technologies of computer dealing with big data is advancing so rapidly that we should be able to do it if we put our mind to it, or basically select one or two postdocs that will be dedicated for the task. That is my sense.
Yeah, it's true, but it's a very unthankful job. These poor postdocs, you know, they spend all of the time doing that, and what they get is a handshake and like, well done, you know. I mean, it is.
There are people doing worse jobs in Google and
that's
Microsoft,
true, yeah.
So, and they're getting paid much. Right. So it's possible, in principle, to entice those companies that deal with data,
yes,
like Google, for example, to be part of this
yes.
endeavor. Yeah. Questions for the panel? Wolfgang over there. We need the...
Well, I can shout. Being a theorist, I would argue that having an image is fine, but having a spectrum is better. Right? Now, we in Europe had set up this PESTO project to do spectroscopic follow-up for transients. Our feeder survey was LSQ, which wasn't a great success because their data pipeline was flawed and things like that. So we didn't get the objects we were interested in fast enough. So we were, for instance, interested in fast and faint. We hardly got any fast and faint objects from LSQ. It's just an example. So PESTO will now run out in a year or so. Is there any plans here among those guys, you guys here, to organize a spectroscopic follow-up in the spirit of what we did with PESTO and on the NTT? I think it would be very important not just to have images, but also spectra, at least for the interesting transients.
I completely agree. This will be especially difficult in the era of LSST, obviously, because there are so many objects. Yeah, and you know, it starts. It starts now with all of these surveys coming online. I mean, we don't have the spectroscopy resources, and yeah, I agree. I mean, as a community, we have not done very well of trying to make this more widely available. Right now, the rich institution with access to, you know, Keck and some of the big telescopes have a big advantage. And yeah, I think in the same way that more and more of these large-scale imaging surveys are getting immediately public, which is a good thing. Hopefully, the spectroscopy will follow soon.
Well, this issue of spectroscopic follow-ups always the big boogaboo of transient astronomy. And things are going to get a lot worse, because between these 1 meter class, give or take factor of 2 surveys today, I think all of us fall at most 10% and probably less than that of all transients that are potentially worth following up. Now, we're all riding Moore's law curve, and our data volumes, data rates are going to go up by orders of magnitude, factor of 10 every 5 years. So what, you know, if you extrapolate it to LSST era, it's LSST. So we're doing LSST science now with more or less scaled versions thereof. So that means that basically when LSST operates, from these smaller surveys, which make spectroscopically viable transients, as they were called, down to 20-ish magnitude or whatsoever, and since the number of spectroscopic assets is not increasing really, we can probably do 0.1% of them. And those are the bright ones. And those are the ones people will do first. And so you can conclude for yourself what will happen to the faint ones from LSST. So that, I think, is the single biggest issue, and in my mind, that's telling us that the bottleneck technology here will be automated classification and prioritization of transients. And even so, we have to be prepared that we will miss lots of good ones.
Okay, we'll move on to other questions.
Yeah, I wanted to make 2 comments. One on surveys. As most of you know, we're doing the DASH survey here at Harvard, which is unique in its time baseline, which is a century, and covering from literally hour timescales. Many of the plates are multiple exposures to, typically cadences of order a week or a few weeks, and basically randomly spaced. It's about a third done. As some of you know, we had a flood here, believe it or not, at Observatory Hill in January, and that has interrupted the whole program, but we'll be back on the air by mid-July and should finish in 2 years. And all the data are being made public. In fact, DR5 will be out in about 2 weeks. So I just wanted to remind everybody that that's another major survey. The second comment on the spectroscopy question, I totally agree that we are drowning in data, and it'll only get worse, and we're missing all of the opportunities to find the most interesting transients. So that has motivated several of us, Ido, George, and I, and about 10 or 12 others, to think about a NASA mission that, if NASA decides to do probe-class missions, which I think is quite likely will happen, but it'll be a decadal survey decision, that we should have a transient spectroscopic observatory, TSO. Neil Garrels in his talk mentioned this yesterday. The concept is a 2-meter class telescope in geosync orbit over LSST, which means you are able to look at a very large fraction of the sky being in geosync orbit, and you're able to do rapid response to not only LSST high priority transients, but gamma ray bursts and everything else, and extending into the near infrared, or in fact even conceivably the mid infrared. So this would be something that you can't do from the ground. And for those who are interested in such a concept, I invite you to join us, because there's a lot of work to do to think about how this could be developed. But I think spectroscopy is absolutely crucial. That's where the science comes from. So we've got to do it.
Thank you, Josh. We'll move on to Shri here, and then James after. And then Ido.
So I'd like to return to the spectroscopy thing, because I think it's a challenge already. And the surprising thing to me is the larger community actually doesn't understand this. Many people have a view that in the LSST era, data will come to their desk. So I'll make a few predictions. First of all, LSST will be the greatest photometric machine we have built. It'll really excel in photometry. Stellar astronomy, galactic astronomy, that sort of stuff will be unparalleled. So if a young person, I'm not thinking of LSST as a transit machine at all. I'd be thinking to do stars and things of that sort. It'll be fantastic, because they spent so much effort, care, to do very high fidelity photometric measurements that none of these surveys are close to it. Okay, probably the best we have at this point is pan-stars, but this will be pan-stars on steroids. That's the first thing. So, my view is that, in fact, if there's an opportunity here, the opportunity is, in fact, to do all the great stuff which requires spectroscopy before LSST happens. And those people who do that will, in fact, be very fine-tuned in the LSST era. And so I think the spectroscopic resource is small, but the way the community is going about is also not all that wise in my mind. It's easy to do a survey now. As Ben says, take a telephoto lens, CCD, a Unix machine, and you can get things. Getting a spectrum for all of those things not interesting. The actual value in the end to me is the paper. I really don't care about the details. What great paper have you written in the end? So I would say the community, us, meaning the core community, is not very responsible about how to utilize the resources they have. They're not small, they're not very large. And I think the real goal here would be to do experiments where you say, I'll try to do this one thing. It can be an experiment of a thing you understand, like 1A, or it's an experiment of a thing you want to explore. So some of those experiments I find are much more fascinating. So the Subaru one-night cadence, where 50 square degrees were investigated 5 times, night 1, night 2, things were found. I think this is a fantastic experiment. So those are the kind of things I think we should think of, and then we can do spectroscopy for those things. And the problem with pesto that was talked about is that's precisely, I would say, a waste of resources. It's a typical European socialistic sort of a thing, and it failed. Socialism usually fails.
James.
Well, first, it's nice to have all the observers up here, so big fan of everything you're doing. I just wanted to talk a few numbers, I guess. So I heard that cost was a issue for making data public and available. And I think that's true if you're talking about images. And in principle, that's what the telescopes are doing. They're repeatedly taking images of the sky. That's terabytes and terabytes of data. It's hard to store that data, back it up, keep track of it. And I understand that is pretty much the primary sort of hardware and computational expense, aside from manpower, in terms of reducing that data. But the actual data products, the things that the theorists will compare to, the spectra, the photometry, the metadata of where it's located, little bits like that, that's a very tiny amount of data. And nowadays, it's actually lightning fast to access the entirety of the supernova data set, as an example. So the number is, I've been making this Open Supernova catalog. I've collected data from all the major groups. The total size of the data set, all spectra, photometry, metadata, is about 3 gigabytes, uncompressed, in ASCII format, so human readable format. So we all got this free USB key at the beginning of the conference. You can fit the entire supernova data set on that twice over, the publicly available one. So I've done an estimate of the private data, so the number of spectra that groups have told me that are not publicly available yet. I estimate it's maybe 4 times as many spectra as what's publicly available. So you're thinking maybe 10 gigabytes of data for the full supernova data set presently. So that data is really, really tiny. The supernova catalog runs on a cloud-based server for about $50 a month is what I pay for it. And I use that to host VoxCarta, which is the other web service I've been running for a while. And it's a few person operation to do this. And so that aspect of it, I think, is actually not expensive at all. So the difficult thing when you're modeling transients is really, you're just interested in what that dot of light is doing as a function of time, right? You want to know how does it get bright and dark and change color as a function of time. And so the difficult thing is removing the host galaxy and any other stray light that's contaminating that photometry. And that's the part I think that, say, Pan-STARRS has been struggling to do in a consistent way, and maybe that's explaining the asymptotic approach. That part is a difficult part that we need the observers to do, and it's really challenging. I think, though, putting all your image files, say, publicly online, while it is nice for other observers to be able to double-check your pipelines to make sure that's being done properly, to us theorists, it's kind of useless, right, to have hundreds of terabytes of images available. We can't really do anything with that. So, I mean, I think that there's multiple levels at which the data can be made public. And so the panel, I'd like to just hear, like, opinions, actually, of, like, what you think is your responsibility to make public and what you're planning to do in the future to make that possible, I guess.
When Armin raises his hand, we only have a few minutes in answer to this question before we go to the...
I'll make it very quickly. So you're only talking about the supernova light curves itself, and that's, of course, a very small data sample. But if you take Pan-STARRS just as an example, just the object and detection database is between 100 and 200 terabytes. So that's already a completely different beast. And if you detect a supernova and you want to get the baseline light curve from other surveys, you cannot go to your database because you have only the supernova. You have to go to the light curves of all objects. So yes, I mean, I agree. When you're going just to the database and the objects, it really helps. But it is still not just as easy as you just said, because you only use the supernova light curves that are published and not all of the other ones, all the other transients and AGNs and variable stars and all of these other things that you also need if you want to do a cross correlation between the different surveys.
So I actually wanted to follow up on the comment that Sri made a few minutes ago, and then the comments he made last night and comments he made earlier in the where I think the theme was that doing these kind of long cadence surveys optimized for type 1a and normal core collapse supernova is essentially boring science at this point. And so I wanted to kind of point the question at Eric, because I was surprised to see that the only public portion of ZTF is a 3-day cadence survey, and I was wondering why that choice to make that boring part the public survey.
Answer your question. That's a great question, Ido. I think there's several ways you can answer this question. The first way is that's what we proposed, and so that's what I'm presenting as the baseline. The second way is, if that's boring for us, it's also boring for LSST, and I think that those of us who are interested in transients, there's still a window in the next year or two to have some influence on the cadence, and so I'm involved, and I know several others are as well, in trying to change that baseline to something that makes more sense for fast evolving things which LSST will find. So we see the public products really as sort of a wake-up call in some ways to try to exert some pressure on the community to move LSST in a direction we think is more interesting. And so similarly, the way we deliver our alerts, we're delivering them as these event packets like LSST does. Well, that requires a broker. Well, we need to build that broker, and sooner than later. So, and finally, I will say, and I'm sure he has many thoughts on this. We have a community advisory committee who are happy to give us feedback aggregated from you and others about what we should do with that public survey. And so I've said this is the baseline. I think if there were no public survey, we would still do that as a portion of our survey. It makes sense to find all the slow, rare things. But there are certainly other models, and we can and should discuss what that should look like.
Okay, last question behind Ido.
I don't think this was done on purpose. I think that the meeting's been very well balanced in the gender arena, but I wanted to ask if some or all of you could maybe give a quick acknowledgement to some of the women who are essential to making these surveys work and the planning of the future ones.
Well, I could start. PTF, of course, Mansi has been central since the beginning, and I expect in ZTF as Sri heads off into the radio realm on his 5-year timescale, I think Mansi is going to be a key driving force going forward. And also Alessandro Corsi, of course, was there at the beginning, and others as well.
Yeah, I'd like to point out that throughout the conference we've been hearing talks, and in particular case of Pan-STARRS, almost all the talks that were given related to Pan-STARRS data by Maria Ragenhild, Suvi, were all women. So there's been many women in leadership roles. We talked about this offline prior to this panel.
Let's see. So our camera scientist who built the dark energy camera, Brenna Flower, she has a big leadership role within the collaboration. Now that the camera's done, she's in charge of the Speakers Bureau, which is responsible for making sure that everyone gets a chance to talk in public and present their results.
I really would like to acknowledge camera people, but also for day crew, because that HSG instrument is so huge, 3-ton weight, above 8-meter. So they have to replace the camera, and without that work, we cannot do anything. So we'd like to acknowledge that.
So with my Pan-STARRS hat on, like Ryan said, I think we have a very strong, lots of women that have done absolutely excellent work and have been leaders in our project. In Atlas, we are a very small group, and so we have a couple of, one postdoc that is female. I think, if you look at the panel itself, it is a little bit one-sided. I'm teensy. So, I think in general, as a community, we should do better. But I also think that in the last years, we have done better than before. So we are hopefully on the right track.
Yeah, it's true about the panel, but if you look at the program, the speakers were quite...
That is actually true, yes.
Like Atlas, we're a small group, but one of the key public features of ASAS is that we have these directed patrols. which look at particular types of targets, and then they send you an email if that particular type of target, something you're interested in, actually flares. The entire portion of ASAS-SN is being led by a grad student at Ohio State named Bianca Davis. So that's a major portion.
Well, let's thank our panel one more time.